Thank you. So good morning, good afternoon, everyone. Thank you for being here today. So I am Devasri Roy, and today we are today hosting our event on our regular symposium series on Rising Stars seminars. So before we begin with the talk, we just follow through a few of our own slides to talk about what our group is doing and who we are. So we are actually a special group, a special interest group. Um, we are focused mainly on AI and ML for insecurity in the broader domain of IEEE TCCN. So our chair is Professor Suba from Stevens, and we are 4 vice chairs. Dola Saha from University at Albany, myself Devasri Roy from ETA, Hanif Rahabari from RIT, and Moinul from George Mason. So today we have Moinul and Hanif with us. So with that, the next, okay. Yeah, so our group is quite large. We just gave a few of the statistics, and it's also growing. In LinkedIn, we have almost 500 members, and there are many ways to get associated with us through LinkedIn. It's the best, and then you can also send us email. We are regularly hosting events. We are regularly looking for people to join us or give us talks. So if you are interested to be the next speaker, you are in that you are on the job market this year, or maybe next year you want to practice your things, talk. So please reach us out. Yeah, you can email us, and you can also find our information online. So these are some of the previous of our activities. So we used to have like a distinguished speaker seminar series, and it actually started during the pandemic. So everything from that time we are actually virtual. It gives us flexibility to invite speakers from anywhere. So at that time we had very topics like talks from various already distinguished professor and scientist. You can see all this information in our website, and the talks are recorded as well. Now this one which we are doing right now, this is like our 5th talk, and I started it from the end of 2023. What is our main goal? So this is like very new initiative from the group, and this started when a few of the new members like I, Moinul, and Hanif, we joined into the group as a vice chair, and we saw recently like the what we go through like the when the senior PhD students are going to find a job in academic or industry research oriented positions, what we go through. So we wanted to like give a platform for the people community to practice their talk. So this is like an opportunity for the students to come and give their talk and be like practice it. And also we want to involve the recruiters in the process as well, and maybe some mentorship and employment opportunities. So overall this is like a job talk, and it is meant to be, should be within 45 minutes because we are on a strict time limit. So we have had these 4 talks earlier. We had speakers from MIT and NIST, then RIT, and also with our last speaker was from UK. So these are a few logistics. Everyone is muted, and please stay muted. And if you have questions, we highly encourage questions. So please, if you have questions, please ask in the middle, anytime in the chat section box. We'll ask them. We'll moderate them at the end. Also, at the end, you can ask again your questions. So with that, we'll just briefly introduce who is our today's rising star. So that's not Mr. André Gomes anymore. So it's Dr. André Gomes. André recently is a postdoctoral researcher with the CCI initiative in the Virginia Tech, and he recently got his PhD in computer engineering from Virginia Tech. And his research interests lie in designing, building, and evaluating networks for reliability, networks that can perform under stringent performance requirement and withstand failures, attacks, and disaster. So with that, I'll stop. And Andre, thank you for being here, and the floor is all yours.
Thank you. Let me share my screen. Okay, should be able to see it now. Thank you for the introduction. My name is André Gomes, and today I will walk you through the work that I've developed during my PhD that goes on how to design mobile networks that can support ultra-reliable communication. I'm going to talk in a moment what I mean by ultra-reliable communication and our approaches on how to design those networks. But just before that, just taking 1 minute to give you a short introduction about myself on top of what was already said. I'm originally from Brazil. I came to the US a few years ago for my PhD. I recently got it from Virginia Tech December last year, so quite fresh. And since January, I rejoined Virginia Tech as a postdoc. I also have some industry experience working as a telecom engineer, and I also have some research internship experience with AT&T Research Labs. Broadly speaking, my research can be categorized into 3 categories. Being the major one, ultra-reliable wireless communication, and that's basically the topic that we are going to cover today. But I've also worked on network softwarization and more recently on reconfigurable intelligent surfaces. But even in those topics, my approach, it tends to be to look at how to make networks more reliable, more resilient. Now, that being said, going back to the topic of ultra-reliable communication, so the first question that we pose is why exactly ultra-reliable communication and what are the challenges to achieve ultra-reliable communication? So the motivation behind looking at this topic comes from this increasing need for reliable and resilient communication, particularly with the use cases envisioned by 5G and 6G in the form of ultra-reliable low latency communication services and hyper-reliable low latency communication services. And the goal here is to enable applications such as fully autonomous vehicles, factory automation, widespread augmented reality. And the challenge in supporting those services generally comes from the very stringent reliability and latency requirements of those services. So we generally talk about reliability for those services as a function of multiple nines, generally at least 5. And by 5 nines, I mean 99.999% reliability. And we talk about latencies in the order of a few milliseconds. And right now, with hyper-reliable latency communication in 6G, we are even trying to push that further to sub-milliseconds. Now, this gives you a perspective that there is very little room for failures or for things going wrong. So the challenge here is how to design networks that can get it right at first time with very little room for failures. So given that context, my research lies on how to design, build, and evaluate such networks for ultra-reliability regimes. Now, a natural way of increasing reliability, reducing latency, is to provision additional network resources to compensate for stochastic phenomena in the network. So for instance, here we have like an example capturing this figure. So here we have a realization of a mobile network. So the dots, the blue dots, they are base stations. And the white area, it's basically like an area where we support ultra-reliable communication with 5 nines reliability. Now, one way of expanding that area is if we increase resources to compensate, for instance, for path loss, fading, interference in the network. So if we provision more bandwidth, for instance, to compensate for those phenomena, we can expand the reach of ultra-reliable communication services throughout the network. Alternatively, we could also like deploy more base stations. So users, they are closer to the base station. It becomes easier to guarantee the performance requirements that we are interested in, and we expand that area of ultra-reliable communication. Now, the challenge here is just like blindly adding resources to the network and hoping that we eventually will meet the target, the reliability and latency targets, is very costly and very inefficient. So we are interested in the question of what what is minimally required to support ultra-reliable communication throughout mobile networks. And with that question in mind, one of the first things that we did was this assessment, this quantitative assessment of the resources required for ultra-reliable communication using 3GPP network models. But before we jump into the results, just establishing some common ground here, some definitions, starting with what we actually mean by reliability. Here we adopted this definition by the 3GPP, where reliability is the success probability of transmitting a certain amount of data within a certain deadline. We can express that definition mathematically. So it basically gives us like this CDF of the user plane latency in the network, and we want that probability of the user latency being less than a certain deadline. We want that probability being greater than our reliability requirement. Now, what is interesting here is we know, like from the channel link capacity, for instance, we know that the user plane latency is related to the amount of bandwidth that we make available for communication. So what is interesting here is when we look at it from the perspective of a resource and we look at this mathematical formulation, we can flip the question and ask a question such as like, what is minimally required to support, to satisfy these requirements? So knowing that it has a connection with the bandwidth, for instance, we can invert that CDF and basically write the minimum bandwidth required to support, to satisfy these requirements as the inverse CDF of the inverse of the spectral efficiency in this case. Now, with this definition in mind, now we have like a means to quantify the amount of bandwidth that we need in the network to support ultra-reliable communication goals. And by ultra-reliable communication goals, I basically mean this alpha when it goes to 5 nines, 6 nines, 7 nines, and when this deadline, it goes like 1 millisecond or so. So with that definition in mind, what we do next is we use simulations to quantify the amount of resources that we need for ultra-reliable communication, and we use 3GPP network models for that. Here we focus on 3 frequency bands, 700 megahertz, 4 gigahertz, and 30 gigahertz, just to represent low, mid, and high frequency bands and what is the resources needed for in each of them. So what we see on the right-hand side, it's basically like the result that we get out of our quantitative analysis using that network model. We do like simulations to obtain the inverse of this the CDF. And we do that for networks of different densities. So we basically have the required bandwidth to support 1, 3, or 5 nines reliability in our network as a function of the number of base stations that we have deployed in the network. Now, one of the things to keep an eye here is the magnitude of resources when we are talking about 5 nines reliability. So here what it gives to us is something in the order of gigahertz of bandwidth to support ultra-reliable communication at 5 nines reliability. And that's generally the level that we are interested in when we are talking about URLLC services, HRLLC services. So, and that's challenging because that's basically beyond what we typically have available in today's networks. We can trade that with network density. And the idea here is the more base stations we have, the closer the user gets to the base station and the easier it gets to support the ultra reliability requirements. But the problem is to significantly reduce that amount of bandwidth, we need to look at deployments that are like 80 base stations per kilometer square, which is unfeasible in practice. So when we look at even dense network deployments of 30 base stations per kilometer square, we are still stuck with this number here of gigahertz. Now, there are like several things to unpack here. The first one that I want to start unpacking, it's looking with more carefully at this number. So first of all, like as we have discussed, it's beyond what we typically have available in today's networks is a challenge. But then just think about it as well. What does it actually mean when we talk about 1 gigahertz or several gigahertz of bandwidth to support ultra reliable communication? What if we only have 100 100 megahertz, for instance. Does it mean that we don't support ultra-reliable communication in the network? If we recall from that previous figure, when we have less bandwidth, it's basically like that area where we support ultra-reliable communication shrinks, but we are still like able to support it to some extent. The problem here is like the way we formulate it, and it's generally formulated out there, is we generally take an expectation over what it takes to achieve those requirements throughout the network. But it doesn't tell us necessarily like if we support it and to what extent we support it. So with that in mind, what we did next was we looked at ways to kind of like unpack that and better understand what are the dynamics of the system. And to do so, we used this framework that is called meta distribution to define two notions of reliability for our system. So the first notion is what we call link reliability. It's very similar to what we defined before if we look at this CDF here. But here we constrain our assessment and in specific location in the network, or if we are talking about a point process, to represent the network and a specific realization of that. And then what we do is we zoom out in the network and we see like what is the distribution of the requirements for link reliability throughout the network. And we define that in terms of the spatial reliability. So spatial reliability is basically the service area in a network in percentage, where we can support the link reliability with the alpha link reliability requirement. So this is better captured by like the figure that we discussed before and this figure here as well. So the alpha is the 59697 reliability requirement that we are interested in. And the eta parameter, the spatial reliability, is basically this fraction of the white regions in our network where we support ultra-reliable communication. So just following the same strategies that we did before, we know that like those two definitions, they are related to bandwidth because they are related to the user plane latency. So we can invert those CDFs to basically get what we got before, the minimum bandwidth to support ultra-reliable communication. Now, the problem here is, like compared to what we had before, things here are much more convoluted. Because when we look at like the spatial reliability, for instance, the spatial reliability is basically like the distribution of the link reliability throughout the space. So when we start like inverting that, we basically have like the inverse of a CDF that is the inverse of a conditional CDF. It's much more convoluted at the formulation here. But what I'm about to show you is we showed that for some network models, we can actually unpack that equation and obtain closed form expressions for that bandwidth requirement. And now the nice thing is it does answer that question. It does like go beyond the limitation that we talked before. So it gives us the bandwidth to support the alpha link reliability at a certain network service area. So for this specific example, we are talking about Poisson networks. So for Poisson networks, I mean, base stations, they are, the way we model base stations in the network is they are modeled as a Poisson point process. And for this system model, we can obtain one expression for the minimum required bandwidth to support the alpha link reliability and the eta spatial reliability. We can even go further and do some simplifications to that formulation with approximations. So we are interested in when alpha goes to 1, again, 0.9999596979. So we can approximate this expression, the denominator, by the first term of the Taylor series expansion. And we can obtain like a more clear kind of expression. Now, one nice thing about this expression here is it kind of reveals this interesting relationship between the bandwidth requirements and the alpha link reliability requirement, where for each 9 that we put as a requirement, we basically have an increase of 1 order of magnitude in required bandwidth to support ultra reliable communication, which already gives us like an idea of that challenge that we were talking before, like the magnitude of the resources, just because it doesn't seem to scale very well when we are looking at multiple lines. So we do like the numerical assessment for this system as well. The interpretation of it that we can get is, if we have like 1 gigahertz of bandwidth in the network, for instance, we can support 5 nines in approximately 10% of the network service area. So that's like the question that we were trying to answer before. If we want to take it like to 40% of the network service area, then we have to go like beyond those gigahertz of bandwidth anyway. So we have like a finer way of assessing the system right now, but we are still stuck with those like high values and that challenge of achieving ultra reliable communication in mobile networks. So what we did next is we look at alternatives on how we could circumvent those requirements to make it easier to support ultra reliable communication services in mobile networks. We particularly looked at this, what we call multi-operator connectivity sharing. And multi-operator connectivity sharing, it basically combines 2 concepts. So the first concept is multi-connectivity. So we allow a mobile to connect to multiple base stations. And the idea here is to have a parallel system. So if we have 2 connections, we duplicate information through those 2 connections. Even if one connection fail, we still have like the other connection to deliver that information. That naturally increases reliability. But we combine that with network sharing, where we allow the user to connect to base stations of different operators. The reasoning behind that is that multi-operator networks, they tend to bring more diversity to your connections, because just think about it, just having multiple connections, if those connections, they are correlated, for instance, no, there is no benefit. One fail, the other one will fail as well. It's likely to fail as well. So with multi-operator, in multi-operator networks, we have like that the connections, they might exhibit more some degrees of independency or uncorrelation between them, just because operators, for instance, they tend to operate in their own frequency bands. They may have like independent base station deployments in the network. So that's the idea here, to explore redundancy from multi-operator, from multi-connectivity, but also leverage increased resource diversity from network sharing. And to get a better understanding of like that intuition that we have in our mind, we did a case study to actually see like where like the benefits of multi-operator connectivity sharing actually lie. This case study, it's a real world data analysis. So we performed a walk test in Dublin, in Ireland, where we had like a backpack. Inside the backpack, we had 3 mobiles, each mobile connected to a different base station, to a different operator, sorry. And we collected data from those operators around the city of Dublin. So it basically gives us like this data set where for each timestamp and location, we have signal strength KPIs for the 3 operators. Now it allows us like to play what would be if we had like a mobile that had like 3 connections, 2 connections, what would be like the benefit. So as we talked before, like the intuition here is we expect some degree of complementarity between the operators, so we can see like the benefit of using multi-operator connectivity sharing. So the first question that we ask is like, what is the degree of correlation between the connections that we have? So we do the Pearson, we assess our data samples in terms of the Pearson correlation of the SNR data samples that we collected. Now, one thing that we see is we actually see some degree of correlation between those connections, which at first glance, it's not good news for us, because as we talked, we were expecting to see things to be more independent, uncorrelated. And the reason here is probably because, just think about it, if we have like a clients, if we are an operator and we have like to make decisions on where to deploy base stations, we generally have like a customer base that tends to be very similar to our competitors. So when we are deciding where to deploy the base station, it's very likely that we will deploy the base stations nearby other operators as well, just because we want to like cover the same, more or less like the same area. And we even have like more extreme cases where operators, they share the same infrastructure. So base stations, they are co-located. But what is interesting here is when we focus on the 10% lowest SNR values in our data set, and we compute the Pearson correlation just concerning those 10% weakest SNR data points, we see that the behavior changes. Now we see like a negative correlation, or we see some degree of uncorrelation between those operators. Now, this is interesting because, again, this is kind of like the behavior that we want. But it only occurs like it seems to only occur in the worst case scenarios. But it's still good news for us, because when we are talking about reliable communication, we are mostly interested when things go wrong, when things underperform. That's where we look like for improvement. When things start generally working well, it tends to be fine. We in terms of reliability, we are generally interested in the worst case scenarios. So this is good news for us, because in the worst case scenarios, we actually see some degree of complementarity between the operators. Another way of seeing it is just plotting the SNR data points, the 10% weakest SNR data points for each operator in a given region in our data set. Now, in some parts, what we see is 3 colors. So the 3 operators tend to exhibit weak SNR. But what is interesting here is in some other areas, we see that one color dominates the others. So in this street, for instance, we have a dominance of the operator represented in red, basically meaning that operator in red underperforms in this street, but the other ones, they provide good coverage. So if we are using multi-operator connectivity sharing here, a mobile is connected to operators in red and blue, for instance, even though connection to the operator in red might not be good enough, the connection to the operator in blue might actually provide like the connectivity that we need in that area. Another way of quantifying it is we compute the expectation of what we expect, like in general case, when we look at all the data points in our data set, but also the expectation when we look at the 10% lowest SNR values. We compute it in terms of the link capacity. We assume certain bandwidth for our system and what will be like the link capacity that we could achieve. So we use this metric called super quantile. It's a very popular metric in risk analysis. So it gives you like a sense of expected loss. So here we use it to compute the expected link capacity, giving the 10% lowest SNR values, for instance. And we compare that like to the traditional expectation where we compute the expected link capacity concerning all the SNR data points in our data set. Now, when we look at the qualitative results, something interesting here is when we compare single operator connectivity, one connection to one operator, and compare it to different combinations of multi-operator connectivity sharing, to the 3 operators, to 2 operators. What we see here is in terms of the 0.1 super quantile corresponding to the 10% lowest link capacities in our network, in our system, we see that by using multi-operator connectivity sharing, we can increase the expected link capacity by approximately 1 order of magnitude. When we look at the overall performance, we do see some like better performance as well when we use multi-operator connectivity sharing, but the gains are much more modest. But again, here, when we are talking about ultra-reliable communication, we are mostly focused on those periods of impaired connectivity. So where like the gains, they approach 1 order of magnitude. So this is not like, this is not necessarily what, as we were defining reliability before, we are not necessarily looking at the ultra reliability regimes here, but it does gives us this indicator that multi-operator connectivity sharing seems like appealing, an appealing way to deal with increased reliability in the network. So with this motivation in mind, we go back to that system model that we had before with the meta distribution to compute the required bandwidth to support a certain alpha link reliability in our network in a certain network service area. And we look at the case where we have multi-operator connectivity sharing. So here we model like the operators, each operator is a Poisson point process. We assume that each operator operates in its licensed band. So there is no inter-operator interference. And for this case, we are also able to derive expressions for the required bandwidth to support the alpha and eta reliability requirements. Now, the expression here is much more convoluted than the other one. It's hard to get that like specific insights of 1 order of magnitude bandwidth. But what we can do with this expression, we can do like a numerical assessment of it, for instance. And for this particular case, where we look at the scenario of dual operator connectivity sharing. So a network with two operators and two connections, one connection to each operator. We see that the required bandwidth in that scenario, first of all, we see that the order of magnitude decreases. So before we were talking about 1 gigahertz to support ultra reliable communication, 5 nines reliability in 10% of the network service area. Here we have that with 1 gigahertz, we can basically support 5 nines link reliability in basically 100% of the network service area. So if we go with the 100 megahertz, which is more aligned with what we have available in today's mobile networks or or the last releases by FCC in terms of frequency bands, we see that we can support 5 nines reliability in 60% of the network, for instance, which is much higher than what we were talking before. Another interesting thing here is, remember that relationship of 1 order of magnitude of bandwidth required to support 5 nines reliability, to support ultra reliable communication. Here that relationship changes. So for dual operator connectivity sharing, what we see here is that instead of 1 order of magnitude, we have 2 nines for 1 order of magnitude. So the system becomes more scalable here. It becomes easier to increase the number of nines and look like beyond 5 nines. We can keep like looking at different systems with more operators, since we saw the benefit with 2 operators, right? The question is, what if we have 3 operators then? What if we have 4, 8 operators in our network? Well, in that case, what we see is, as we would intuitively expect, the more operators, the more connections we have in this multi-operator connectivity sharing arrangement, the easier it is to achieve ultra 5 nines reliability in our network. So here we are assessing the 5 nines link reliability requirement. So the red line is basically what we have in single operator, single connectivity scenario, as we traditionally have in today's networks. And the other ones are the different combinations of multi-operator connectivity sharing, the dual operator connectivity sharing, as we discussed before, and then with 4 operators and 8 operators. Of course, like the more operators, the easier, the lower is the bandwidth requirement. But what is interesting here is the delta gain is quite higher when we go from 1 operator to 2 operators, which is good news, because it indicates that even in network sharing arrangements with only 2 operators, we can already experience significant gains. So we don't need like to grow that network sharing arrangement to many operators. Another challenge that I want to highlight here when we are talking about ultra reliable communication is this challenge of assessing ultra reliability regime. So we started talking about qualitative results based on 3GPP network models where we did simulations. And then we moved on like to scenarios where we were able to derive expressions for the required amount of resources for ultra reliable communication. Now, the problem is obtaining those closed form expressions, it might only be feasible for some network scenarios. So for more complex network scenarios, we may still need to rely on like simulations or empirical assessments, as we did at the very beginning. But there's a challenge over there. There's an intrinsic challenge to ultra reliable communication in this case. So when we are talking about 5 nines reliability, for instance, 99.999%, we are interested in the network conditions that occur with the probability of 0.001%. Basically meaning that we are talking about if we are running simulations, we are interested in the events that tend to happen once every 100,000 times. We want some confidence there. So we want to say, yeah, I want to likely capture that event. So we would run like even more simulations, and soon we are talking about like collecting millions of data samples or running millions of simulation iterations, which of course, depending on the scenario, can be quite expensive, and depending on the application as well. If we are collecting data to do like to select the rate to transmit in a certain time slot, we may not even have like the time to collect enough samples to characterize the channel and then to make the rate selection properly to achieve the multiple nines. So there's like this challenge on how we assess the ultra reliability regimes, because we need massive data for that. So we in this work, we approached that problem and we look at ways on how to circumvent this challenge of massive data collection for assessing ultra reliability regimes. And we look at extreme value theory in particular as a way to facilitate assessment of ultra reliability regimes. And what extreme value theory gives to us is it gives us like a framework to model the tail distribution of random variables. For instance, one of the theorems that we encounter in the extreme value theory framework is this theorem that tells us that for a large number of distribution functions, we have that the excess tends to a certain distribution. And here's what I mean by the excess. So we have a certain random variable. It could be the inverse of the spectral efficiency that we were assessing before. And we specify a certain threshold. And the excess, it's basically like we look at the values beyond that threshold. It's actually the difference between the threshold. It should be lowercase here. It's like the difference between that threshold and what we have beyond that threshold. But this theorem tells us that that excess for a sufficiently high threshold tends to the generalized Pareto distribution. Now, this is important information because once we know the distribution of a random variable, we can like try to find the ways to do approximations or estimation. We can leverage that information, right? And that's basically what we do here. So with that information of the excess, we use it to look at the very extreme tail of the inverse of the spectral efficiency. And we use that information to obtain the required bandwidth. So we have like a certain number of samples. We specify the threshold. We compute the SS. We use this data set here that samples that beyond the threshold. We use them to estimate the parameters of the generalized Pareto distribution. And once we have that estimation of those parameters, we use this information, we use the CDF of the generalized Pareto distribution to go back to our original problem and look at the tail of the inverse of the spectral efficiency and how to compute the required bandwidth to support ultra reliability requirements. So here, what we have here in the lower right-hand side is the number of data samples that we need to collect, number of simulation iterations in our case that we need to run to assess reliability requirements in the order of 2 nines, 3 nines, 4 nines, 5 nines, so on and so forth. And we compare our proposed approach with benchmark approaches that we have in the literature. Now, what is interesting here is when we compare the performance in terms of 1, 2, 1, 2, 3, or 4 nines, we see that our approach tends to underperform um, baselines. But what is interesting here is when we go beyond 4 nines, our approach tends to perform better than the benchmarks. Now, two things to say here. Like one of the reasons why it tends to perform not so well in this region is when we are talking about extreme value theory, this is a framework for extreme tails. So when we are talking about 1, 2 nines, that not might be the necessarily appropriate use for that tool. Second, this region here, it's basically the region that we are most interested in. So ultra reliable communication, 5 nines, 6 nines, 7 nines. So this is the region where we do see the gain of using our approach based on extreme value theory, and we can facilitate assessing ultra reliability regimes. So as a summary, in this presentation, we covered this notion of reliability coverage, this framework that we developed using meta distributions that allows us this finer grained assessment of network resources to support ultra reliable communication. We discussed that the requirements, they tend to be beyond what is typically available in today's networks. And we discussed multi-operator connectivity sharing as a means to facilitate ultra-reliable communication in future mobile networks. We discussed about that relationship between one order of magnitude, one order of magnitude increase in the required bandwidth, and how multi-operator connectivity sharing could reduce that to 2 nines, one order of magnitude increase, for instance. And we also discussed like this natural challenge of assessing ultra reliability regimes. There's this massive data collection required to estimate the very extreme tail of a random variable to assess the ultra reliability regimes, where we applied extreme value theory for that. Looking a little bit ahead, most of this work has been on looking at like the spectrum requirements of ultra reliable communication services, which are services that we are envisioning for use cases such as fully autonomous vehicles, factory automation, widespread augmented reality. So services that we are envisioning that we want to enable in the near future. But then the question here is like, we look at it from this general umbrella that is best of URLLC and HRLLC that gives us some some target parameters to study. But even under that umbrella, like those services that I mentioned, fully autonomous vehicles or widespread augmented reality, they have like slightly different challenges for each one. So for one, like the amount of data might be, we need to transmit more data than the other, but one might have like a higher reliability requirement. So one of the things to do next is it's going to specific to specific services and assessing what are the spectrum needs to actually enable those services in 5G or even 6G. And along those lines, the NTIA in the US recently came with this national spectrum strategy where like the goal is actually like to look at ways of like getting ready for the spectrum needs of tomorrow's communication services. And another thing that is quite important here is how to efficiently use the spectrum. So just to give one example, when we were talking about that region, the required spectrum to achieve network-wide ultra-reliable communication, we discussed about like this tension of like it's easier to support ultra-reliable communication when we are closer to the base station, and then it gets harder as we move further away and goes to the cell site. But so that's just to say that like in that region where it's easier, for instance, it might be that just allocating that amount of spectrum becomes inefficient. So better ways to do like utilization of the spectrum to allow coexistence of different services in the network. And with that, I end my talk. And if you have any questions, I'm glad to answer.
All right, so I see we have a couple of questions. The first one is from Doganalop. I'm not sure whether I'm pronouncing it correctly. So these are quite interesting multi-connectivity results. Do you expect similar results if we would be able to connect different Wi-Fi 7 access points operating in different frequencies simultaneously, such as 5 gigahertz and 6 gigahertz?
The results that I discussed, so talking about the different frequency bands, I would just refer to this slide because here we assess like the different frequency bands. Well, those results here to some extent, they are agnostic to the network protocol to be used, in the sense that here we did like this first order approximation study where we assumed that things are transmitted at the Shannon capacity, for instance. So to that extent, it might suffice the Wi-Fi 7 requirements as well. The only thing here is regarding those, well, where things change here, it's regarding the deployment of the access points, of course. That probably leads like to different results. Regarding the frequency bands, I mean, yeah, it's hard to say without modeling the deployment of the access points for the Wi-Fi, like probably indoors. But one of the challenges that we get out of this analysis is those gigahertz of bandwidth, if we actually like need them to achieve ultra reliable communication, in those bands that you mentioned, the 5 gigahertz and 6 gigahertz, they are basically unavailable for those bands.
So there is one more question from the same person. Have you also evaluated trade-offs between reliability gains and energy consumption in such multi-connectivity scenarios?
That's a good question. Energy consumption, no. We have evaluated the trade-offs regarding the network load. I'm referring to this work specifically. Those results, they are not presented here in this presentation, but what we did was this evaluation of, because think about it, multi-connectivity in general, not only multi-operator connectivity sharing, multi-connectivity in general, we increase the number of connections in the network, and to some extent, those additional connections, they will dispute network resources, so they will consume more network resources. And to some extent, we do have like this tension of, we have more connections to take care, and then we have less resources available for each connection. And then the benefits of multi-operator connectivity sharing, they might not be that attractive anymore. So for instance, like in this study, we did study FDMA systems where we have like frequency division, multiple access. And at some point, if we are introducing more connections to the base station and we need to divide those resources among the new connections, then at some point, bandwidth for each connection becomes scarce, and it actually hurts the system.
All right. So we have one question from Hanif. Hanif, do you want to unmute yourself?
Sure. Thanks, Andre, for the talk. I understand the benefits of the proposed multi-operator approach with regards to the coverage and making sure that the area is covered. But the fact that these multiple operators in the proposed approach have to send perhaps the same or similar information to the same receiver wonders me what's going to be the impact of this approach on the throughput of each of the operators, because now the operators have to send similar information to one user rather than each operator send its own data to its own users. So what's the impact of this approach on that on the throughput of
Yeah, I
the
mean, if you are
individual
computing,
operators?
I'm sorry, if
Yeah, go ahead, please.
if you are computing the throughput in terms of like the unique information that you send given a certain time window, it definitely hurts, right? So, but just like here we were looking specifically at the case for users that might be interested in increased reliability in the network. So we are talking about like specific applications such as like remote controlled vehicles, for instance. So the target number one is just to guarantee that that information arrives there. So in terms of like unique throughput, it does it does hurt the performance. But then the benefit comes of guaranteeing that certain information gets to the receiver with a certain deadline.
So basically, I'm trying to understand what could be the motivation for the operators to adopt this. So perhaps for certain applications that the user is willing to pay perhaps more for the service, and having subscription to multiple operators, then the operators would be willing to perhaps, support such approach. I'm trying
Yeah.
to see what, in terms of the
That's
policy making and
yeah.
economic aspects of this, how it should be played out, how one could convince the operators to adopt this approach.
So that's an interesting perspective because generally speaking, yeah, what's the motivation for operators to, let's say, like come together and work together? I would say that the motivation is probably very that's probably a very impractical scenario, like to expect the operators to come together for a common good. But what we have to imagine here, and that's generally what people tend to imagine when we are talking about network sharing. But a more interesting scenario is we can actually like build business models on top of this approach that we are proposing, right? So I'm thinking about like Google Fi in the US, for instance. Until a while ago, it used to operate on top of so it's a mobile virtual network operator that used to operate on top of a multi-operator network. So they were leasing infrastructure from three major carriers in the US. So you could have like virtual mobile operators that target a customer base of applications that are mission critical related. Remote controlled vehicles, for instance, let's say like cars or drones, or a factory that wants to automate its machinery using wireless networks. So we could talk about like this virtual operator that comes to give service to that customer base, and it leases infrastructure from this multi-operator network. So in my perspective, at least, that's like a more feasible and practical way of looking at it, harder than actually like convincing operators to collaborate with each other.
Okay, sounds good. Thanks.
So I see Jacek has turned on his video. Do you have any question?
No, thank you.
Okay, all right, sorry.
Thanks for the introduction.
Okay, so the next question is from Hassam. How using AI/ML can improve URLLC in 6G?
Well, so that's like, perhaps I should have like articulated it slightly better, but one of the potentials that I actually see is regarding this efficient use of the resources, for instance, especially when we have the coexistence of multiple services in the network, how to actually like balance the different requirements of different services, and having them operating, sharing the same resource, the same spectrum, the same bandwidth, for instance, at a given operator. We were talking about the virtual operator case, for instance, as I gave an example of Google Fi. So one example would be like ML to manage the required resources at a certain time to do like the slicing for that virtual operator, as an example.
Okay. And the last question is from William. operators come together for a common good. Okay. Question. Will they have to have incentive and regulatory policy? Okay, so it's not actually a question, it's more of a comment.
Yeah, I agree. I think it's hard like to convince operators that they will, operators that are competitors, that they will benefit coming together for a common good. But as I mentioned before, it's you can also you can approach it from a different perspective, right? Like you can envision different business models, such as a virtual operator operating on top of a multi-operator network, and what is the benefit of that?
I'd
So,
agree. That's the right way to think about it. I'm an economist, so
Okay.
I think that, and I understand this talk was technical. I'll be looking at your papers. I think they're interesting, and you talk about a lot of really good important stuff in this space. One of the things I'd be interested in, and which again is a building on this, is the enforcement issues on the reliability. So if someone builds this stuff, how would you know that actually what they say is there is actually there? Okay, because
Yeah.
you can't do it. You can't regulate on the basis of outputs. You have to regulate on the basis of inputs. Because if you ever observed violation of your reliability claims, then those are events you won't observe, right? So
Yep. I
yeah,
agree.
there was work in this that one of the future internet architecture projects. This is one of the things that came up, and there's a lot of stuff, and it has to do a lot to do with measurements, the kind of measurement issues that you might make available and what you might make shared to assess that. Like for example, and I don't know in this work, I haven't looked at this. This is how much of this could someone validate? Maybe this is the zero proof, the zero information proof stuff. That I don't know if you've looked at that and how that impacts what you're talking about. Like what someone could use to verify that in fact your radio, your algorithm has done exactly what you say you've done here. Because they'd have to be able to do that ex ante, not on the basis of actual performance.
Yep. I agree. I mean, it brings like interesting perspectives.
Zero knowledge proofs. That's what I meant.
Yeah.
Yeah. So I mean, like, there is some stuff you might be able to do by simply, and it would be like simple. Are there simple things you could do to make it as you move this into code or whatever? And these are details. This is sort of not what you were talking about. At any rate, it's the kind of stuff I think about.
Yeah, no, fair enough. I think that those are quite interesting, like the way of like monitoring and guaranteeing it. What I want like to bring up to this conversation, it's just this slide that I'm showing here is like this work. It's I mean I think that's like the closest to that point of actually like monitoring and making sure that you are meeting the reliability requirements, because one of the ideas here is that you could also use this extreme value theory framework. It's like you are actually monitoring the performance, but then the thing is you try like to predict possible violations before the violation actually occurs in ultra reliability regimes. And that's important, right? Because as you mentioned, I mean, if you just rely on looking at the past and look, okay, a violation occurred, but then violation already occurred, so what can you do? There isn't much to do in that case, at least not like from the past.
Right, and I think that if you wanted to move this into sort of the economic domain, that thinking about it in terms of contracting, so like the MVNO perspective, I think is the right one, and then it would be thinking about it as what would be contracts that an MVNO would sign with the underlying network, such that it would actually be able to reasonably expect to get the benefits that your solution delivers, and what would be required to have those contracts work. And some of that could be looked at. I mean, obviously, game theory would be the sort of way that you sort of one way to look at it. Another way would be sort of mechanism design stuff. But anyway,
Well,
good
thank you
work.
for the input.
All right. So we are over our time limit. Thank you, Andre, for the excellent presentation. I learned a lot. And the beauty of this kind of knowledge sharing is that you might already got the next 5 to 10 years of research problems, right? Especially network economics. So we all have this. questions about how to implement this and how to assess it from the network economics perspective.
Yeah,
All right.
oh,
Yeah,
sorry.
go ahead.
Well, thank you. One last thing before we go. Yeah, if you have any questions that I haven't answered, please feel free to reach out. You have like my email. Yeah, you are more than welcome.
All right. And then take care. Bye.
Thank you. Bye bye.